Hi everyone. Today we're going to study the Handshaking Theorem for undirected graph. Let capital G equals the elements capital V and capital E be an undirected graph with small e edges. Then 2 times E equals the summation of degree of V or vertices, and this small v is an element of capital V. We have remarks here. This is the first one. An undirected graph has an even number of vertices of odd degree. Second, the sum of the degrees of the vertices of an undirected graph is even. This is the statement corresponding to our formula here. Example 1. How many edges are there in a graph with 10 vertices, each of degree 6? The sum of the degrees of the vertices is 10 times 6, which is equal to 60. It follows that this 60 is equal to 2e. This is the formula of our handshaking theorem. The e here is the number of edges. Simply we divide this by 2 to get the value of e. Therefore, e equals 30. We have 30 edges. Example 2. Draw a graph with the specified properties, or explain why no such graph exists. We have here 3 scenarios. Let's begin with the first one, a graph with 4 vertices of degrees 1, 2, 3, and 3. So we have 1 plus 2 plus 3 plus 3. We have 9. And this is an odd integer. Since the total degree of a graph is always even, hence no such graph is possible. For the first scenario, we say there is no graph. Second, let's draw a graph with 4 vertices of degrees 1, 2, 3, and 4. The total degree of the graph equals 1 plus 2 plus 3 plus 4 equals 10. This is an even number, so the graph is possible. In fact, there are 2 graphs with 4 vertices of degrees 1, 2, 3, and 4. The first graph is this. This is the second graph. We can see that A has 1 degree, B 2 degrees, C 3 degrees, and D 4 degrees. In the second graph, A has 1 degree, B has 2 degrees, C has 3 degrees, and D has 4 degrees. These 2 graphs we will copy in our second scenario. Third scenario, a simple graph with 4 vertices of degrees 1, 2, 3, and 4. Suppose there was a simple graph with 4 vertices of degrees 1, 2, 3, and 4. Then the vertex of degree 4 would have to be connected by edges to 4 distinct vertices other than itself, because of the assumption that the graph is simple, meaning there must be no loop nor parallel edges. This contradicts the assumption that the graph has 4 vertices in total. Hence, there is no simple graph with 4 vertices of degrees 1, 2, 3, and 4. So simple graph is not possible in this case. For scenario 3, we write no simple graph. These are the final answers. Example 3. In a group of 15 people, is it possible for each person to have exactly 3 friends? Suppose that in a group of 15 people, each person had exactly 3 friends. Then we could draw a graph representing each person by a vertex and connecting 2 vertices by an edge if the corresponding people were friends. But such a graph would have 15 vertices, each of degree 3, for a total degree of 45, and this 45 is not an even number, which is not possible. Hence, in a group of 15 people, it is not possible for each to have exactly 3 friends.